finding time to join our second afternoon sessions, which will have 3 presentations. And we start with Eugene. Eugene, you were just introduced by Vicky anyway. And so let's go straight away, and I'll see you back for the question and answers.
Okay, thank you, Eric. Well, good afternoon, everyone. It's my pleasure to be here to introduce some of the latest technology developed by Potec Fine Chemicals. The topic of my presentation today is about optimizing structure of low viscosity synthetic fluid, specifically for improving the EV transmission lubricant performance. And before I begin, just a little bit of background information about Potec. Potec Fine Chemicals, we are a Taiwan-based company. We are a research-oriented, innovative chemical synthetic company that manufactures primary Group 5 ester technology. Our main area of focus is in lubricants, personal care, and polymer additives. And since our inception in 2000, we have been dedicating significant resources in research and development. More than 20% of our staff are dedicated to research chemists, engineers. We also pride ourselves in developing our own in-house molecular modeling technique with the state-of-the-art tribology labs to help us develop novel and highly effective products for this market. Here's just a quick overview of our global presence. As you can see, right here, Potec, Taiwan is basically, this is where we are headquartered with all our manufacturing operations. And we have 5 offices across the globe with 7 warehouses scattered across Taiwan, Japan, China, Europe, and US. And here in Southeast Asia, we also work with some of our distribution partners to help provide some of our ester product, base oils, to this market. So, EV, obviously, as some of my previous speaker has actually mentioned, it's growing very fast. It's becoming a reality that that would be part of the critical part of the equation to solving global warming, with carbon emission as one of the key criterias, because with the BEVs, less than half is of carbon emission comparing to driving a conventional gasoline vehicle. So under the circumstance of energy saving and energy efficiency, as well as some of the regulations in place, the demand and the market share for hybrid and EV vehicles are greatly increasing. And if you can see on the lower right-hand side of the chart, the percentage of EV and hybrid are expected to grow significantly in the next 5 to 10 years. Okay. So when it comes to EV transmission fluid, comparing to some of the conventional transmission system, it's not just about having the lubricity performance, the protection to the gear. Now you're introduced with a second set of variables where dielectric property becomes very important. So if you look at a ideal EV transmission fluid, you want something that have good heat management, good dielectric property, thermal property, meaning stable in the high temperature environment. And then obviously the key is lubricity, keeping the transmission functioning and running smoothly. And then another aspect which weren't introduced before is material compatibility, because now you have the fluid in contact with the motor and electrical components, so you have rubber material, things of that nature you have to consider that doesn't impact, as well as copper wire. You don't want to see copper corrosions. So it's really a combination of a dielectric fluid and a traditional transmission fluid. So what are some of the key criteria? Well, low viscosity being one, because you want to be more energy efficient with less drag. You also want to have low volatility with NOAC, so you want to keep it stable. You want to have enough working fluid inside the system. Low friction coefficient, obviously enhancing the performance. Good oxidation stability, as mentioned. And in terms of electric property, you don't want to have conductivity happening. You want to have good thermal management, and as well as oxidation stability, because with a motor, you're running at very high RPM, generating a lot of friction in the process, so you want to control that. And then, as I mentioned, material compatibility. Okay. So that said, in terms of specific performance, we want something with high extreme pressure and high wear properties. We want a product that can have good friction control. Obviously, having a low viscosity, you're faced with challenge of evaporation, NOAC. Also, you have to have the heat transfer cooling efficiency to help keep the motor and the transmission running at a right temperature. Oxidation, sludge control is always critical, and then electrical property and resistance. And as I mentioned, additional to material, anti-corrosion is also critical. So why ester? Well, with ester, first of all, it's made of the combination of different fatty acid and fatty alcohol reacting. So you have a lot of flexibility in determining its structure, determining its performance, and even designing specific viscosities for different conditions. And in our case, we want very low viscosity. So we're able to reduce the viscosity significantly, at the same time did not sacrifice the lubricity performance. And also compared to the hydrocarbon-based fluid, usually the low viscosity ester, not only having better lubricity, it also has better NOAC volatility. So if you can see in the chart, this kind of compared the different type of base fluid. We got the group 3, the PAO, the monoester, diester, and polyols. And in general, in these three groups or esters, they tend to have very little NOAC. The performance-wise is very stable, meaning it doesn't evaporate or burn out in the process. And then we also look at the EP with the Felix fairly low. The ester chemistry by itself has stronger performance with the film thickness, and also under the different wear load, you can see that polyester typically has a better performance versus diester and monoesters. In the case of PAO4 and group 3, it failed the testing, so meaning that it could not withstand the load when it tried to do the ping and V test. So for heat transfer comparison, what we're looking at is really trying to understand the relationship of the lubricant, its characteristics, its features, versus heat transfer probability. And in our design, we realized that there's a high correlation between density, obviously heat capacity, viscosity of the lubricant. So with that in mind, we were able to design product with a higher density and maintain the good heat transfer performance. At the same time, you can see here, in terms of viscosity, we have a much wider range to work with. We can go down to a very low viscosity product. And this is kind of our modeling for in-house design to simulate and calculate the performance of heat transfer. It's actually a very complicated model, so I won't go into detail, but it takes into account of the chemical structures, a good contribution from different molecules. Looking at some of the outcomes with these, we're able to quickly identify good candidates for different transmission fluid requirements. So based on our development, we have a series of products. We call it the EV series, just to make it easier to identify. So here we have a very low viscosity EV1 Plus, EV2R, EV4 Plus, EV6, and actually we compare it corresponding to PaO2, PaO4, PaO6. As you can see here, with the heat transfer coefficient, most of our esters have better performance within its own same viscosity grade. As well as if you look at the heat transfer coefficient, this is comparing with some of the conventional esters in the market today, maybe something more like currently in use in the transmission fluid. We have designed a product that will have better heat transfer coefficient, even among the ester classification. So the benefit of ester, obviously, we tend to have product with a higher flash point, so we can work in a higher temperature. The breakdown voltage within the same viscosity grade of mineral oil and PaO is also much better. Our fluid can also use greener feedstocks, basically vegetable-based derived materials to increase the renewability. And at the same time, it's kind of help us to also achieve the sustainability aspect of having a product that's greener and more environmental friendly. So I talk about breakdown voltage and corrosion. So we did a series of tests to look at the breakdown voltage difference of the group 3 PaO and esters, and looking at product with low water content, moisture content, and as well as slightly higher at the 40 ppm and 110 ppm. So you can see that even when there's moisture introduced, ester tends to be very stable in terms of its breakdown voltage, whereas the other type of hydrocarbon-based material, once you increase the moisture content, you see a significant drop in its breakdown voltage. So that's, one thing critical to think about is that when you have a system that comes into contact with an electric motor, you want to ensure that it has good breakdown voltage or electrical resistancy performance. As we can all imagine, in a moving vehicle, it's not going to be completely vacuum sealed. It's going to be susceptible to some moisture coming in. So that's something to consider. And as far as the copper corrosion test, on the bottom right, we did the standard STMD 130, 80 degrees C for 336 hours. Looking at 3 of our products, basically, it all passes the copper corrosion with a very good result. No corrosion shown in the copper strips. In terms of oxidation stability, we use the OOT measurement to look at the different temperature level where the heat goes through with the presence of oxygen. As you can see with the EVs products that we design, tends to have a relatively high temperature range, and ranging from about 205 all the way up to 215 degrees Celsius. So very good high temperature range to work with. As far as volatility is concerned, you can also see that obviously it's expected with a low viscosity, you're going to have a high loss, evaporation loss in the process. But in something in the ISO 2 grade range, we tend to maintain a good percentage of the working lubricant. Okay. So obviously, traction very important. So we conducted MTM traction tests on our product versus the PAOs. In general, the lower viscosity obviously tends to have lower traction, both in the cases of PAO and esters. But if you put the two type of base stock together, you'll see that in general, the ester of the same viscous grade tends to have lower traction. So that's also very important when it comes to designing a transmission fluid. And material compatibility, we conduct two type of testing in-house. One is a modeling, a simulation where we input different type of material, looking at the composition versus our chemical structure, and we're able to quickly screen some of the candidate, looking at the affinity of different materials versus our base fluid. In addition, we do the physical testing to see whether there's any swelling, whether there's any losses or changes or brittleness to the material. So obviously, being an ester, usually with the plastics, we have different groups of product that we can work with. The ones that are really not acceptable are the PVCs, the nylons, and for the rubber. MDF is kind of in between depending on where you use this material, but the rest of the EPDM, those are not quite easy to work with when it comes to interaction with ester. But nevertheless, we still have a range of rubber and plastic material that can be used in the system without causing any issue by introducing a ester-based transmission fluid. So in conclusion, the BEV market share is increasing significantly due to the policy and carbon emissions and energy efficiency. Potex optimized low viscosity ester based on our state-of-the-art molecular modeling outperforms the hydrocarbon-based fluid to realize a higher efficiency in terms of battery immersion cooling, EV transmission fluid. Our spatial design ester not only offers excellent heat transfer, dielectric property, lubricity, oxidation stability, but also feature renewability and biodegradability, which are important when it comes to environmental protection. And I kind of summarize in a little chart here in the bottom where basically we're comparing the critical aspects or performance elements of different group or different types of base stock. And obviously here in our case with our EV series, we're able to design chemistry that really outshines our competition with a lot of these performance requirements. So with that, I'd like to thank you for your time, and I'll let Eric take over to see if there's any questions to ask.
Yeah, I think. Thank you very much, Eugene. This is, of course, very much a presentation that hits what we are currently working with, the challenges in the lubricants industry with the emergence of more and more EVs. We have Slido up, so usually it takes a little bit longer until we have questions on Slido because people tape on their phone. From my perspective, looking at this, you talked about the let's say the biofriendliness. Do you have any ideas on the product carbon footprint? Is it a negative product carbon footprint we are looking at?
Well, I mean, it's not a negative product carbon footprint because in the process we have to consume energy.
Yeah.
But nevertheless, in general, the carbon footprint will be lower if you were going with a hydrocarbon-based material.
Yes.
That said, at Potec, we have just finished conducting our Scope 1 analysis on carbon calculation. We're in the process of getting all the data from our suppliers and our partners to get the Scope 2, and hopefully with that we will be able to provide life cycle analysis with the total product carbon footprint for our customer, so that they can realize that having a greener chemistry does also have additional values.
Then I looked at it and knowing what some of the OEMs are thinking about. I mean, this product comes into an integrated system where you have the gearbox, the motor, and the inverter in one system, and the product can cater for everything. Some of the EV manufacturers want to go one step further, also want to include the battery into that same system, or at least use the same fluid to prevent risk of fluid mixing. Is that something that this fluid could do?
Certainly. I mean, the base stock is designed to work in a EV system. So similar concept, the base stock can be applied to battery cooling. But the other aspect you have to look at is how that heat transfer performance is, and also in terms of the power density is critical for battery manufacturer to look at that.
We have a few questions on Slido, and this basically links into that your view on immersion cooling of EVs, and how far is the progress?
Yeah. Well, I think it's still an ongoing process. A lot of OEMs, they tend to stick with the existing technology, some of the indirect cooling jackets or using air cooling. But we also see innovative company that trying to edge the competition by looking at single-phase immersion, where it's able to control temperature more evenly throughout the system. We, have an advantage based in Taiwan that a lot of these manufacturer component to whether it's data center or battery or energy storage are located. We're actually working with a lot of them, and in addition, we're working with UL right now to set a standard for safety. So that's also very important. So when it comes to battery, you also have a safety concern. That's another factor. As far as the second question on biodegradability and being green.
Association to green, what is green?
Well, I mean, I think people tend to think green as in has to be 100% plant derived. But we look at it as sustainable, renewable. So I think there's a lot of innovation in the industry that even, when it comes to some of the petroleum product process, they do the recycle material, they do biomass processing. So by green, I think it should be trying to achieve a lower carbon emission. And obviously, the goal is to be sustainable. So if you can go 100% sustainable, that's ideal.
Yeah.
But it really also has to depend on performance, because if the lubricant structure based on 100% green chemistry does not quite meet that requirement, then it still does not serve that purpose.
And that's a very technical question about the breakdown voltage, and whether you can give any insights into the mechanism why your ester has a higher breakdown voltage than a mineral base oil.
So unfortunately, I'm not able to respond to that question, but we have a booth. We do have our technical guys there. So I welcome you to stop by our POTEC booth and pick the brains of our researchers about why it is. But from my understanding and perspective, ester tends to hold moisture to a certain level, and then from there it doesn't go any more. So maybe with a mineral oil base, you're talking about a couple percentage, whereas in ester, you're talking about 500 ppm. Mm-hmm. So,
I think, anyway, it was a good recommendation for the audience. Please pass by the PATEC booth, have a discussion with the people there. We have here, how can you optimize the design of an ester-based immersion cooling system to minimize fluid leakage and ensure uniform heat distribution? I think first of all you have to define the seal material. But that was very clear. Yeah? You have to work with whoever designs the system. That system ensures that no incompatible seal material is used.
Yeah, that's correct. So obviously the design of the system is critical, and the other part, as Eric alluded to, we need to do compatibility analysis to make sure that once we introduce this working fluid, it doesn't change, it doesn't impact the performance of the design. So that is also part of optimization is you tweak it around the affinity of the working fluid with these material to make sure that you find a right balance.
I think it's a good subject anyway, because in my career, in the beginning, it was always the OEMs put something and you have to cope with it. I think we're now more into a partnership approach where to optimize the system together gives you a lot more opportunity to improve efficiency than living which was given to you. Yeah.
That's correct. Yeah. So as also echoing our keynote speaker from dinner last night,
yeah.
Let's work together. Let's find a solution.
Exactly.
Let's put aside the competitive nature of it. Just try to do our part to make the world better.
I think it was something that echoed during the conference as well, where we have no competitive constraints. We should partner more and work together to make the world cleaner, to make the world better.
Yes.
Yeah. Okay. I think that's it. We're done with it. Eugene, thank you very much for this presentation. Very, very interesting and definitely a highlight. Thank you, and yeah, I'll see you later. Or you have to leave.
Tomorrow.
Tomorrow.
I'll be around. So
I'll
if
see you
anyone
tomorrow.
want to speak further, come to our booth. I'll be there, and then our team is there to help answer the technical questions. Thank you.
I see our next speakers are already waiting, but let me just breathe and give me a moment.